Okay, everybody, let us start. So we're actually talking about the vanishings gradient last time, right? I mean, yesterday. So, and we show one way to fix, which is a ResNet, right? Or we can use any exponential integrator. Oh, I'm sorry. Exponential, any activation function, different one. And you need to be careful. One of them is actually the ELU is actually quite good. Okay, so let me back to the motivation again. Quickly go through. So remember that we want, this is what we want, right? We want our function, and I using a very simple loss function there, right? Where we minimize the difference between the function f, right? Which is our, what, that could be anything, right? Our case, we look at the neural network, but it could be anything. And then g is something that we don't know, right? And ideally, this is what we want. We want to minimize, we want to look for the best f, or in this case, because f is parameterized, right? F is parameterized by these weight and biases. But the more generic idea is that we look for among on the function that we are interested in, right? This is more general idea. We want to look for a function best in this sense, right? That is minimize some distance between the unknowns and the best. Okay, so but unfortunately, there's many things that we don't know about this loss function, and that does not allow us to actually do the actual computations. The good thing is that in the practical situation, even though we don't know G, right, we typically have some observation about G, right? In our case, we assume that we know that a certain number of points. In this case, we assume that we have like m points, right? And at each point, say it again. Recording? I don't know. I mean, that's the. Record this from. I think they must be there's something behind. I don't know. Yeah. But good. I think they know what they're doing. I think if I go outside, it shows something. Anyway, I think that don't worry. It's not our responsibility. Yeah. So we assume that we have like a few points. In this case, we have m points, and at each point. All right, so sorry, we just come back here. Yeah, so we assume that we know, a set of points, right? Of course, we need to have the information about things that we don't know. If we are really ambitious and greedy, that I don't know anything about that, but I want to construct that, that's impossible task. Right? That's not practical. So we have to know something. So it's not a really limitation, right? We need to know something. Okay, so today we're not talking about neural network, right? So the first thing that we notice is that, of course, that is what I want, and this is what I can write, right? And notice that I put 1 over n here as well, and this is kind of natural, right? If you really want to ask me a question, you said, if I have n points, why should my loss function look like a sum, right? Why should my loss function a sum, not a product, or not something else, right? We should immediately have a question, why we have a sum here, and why 1 over n here, right? Is it a good approximation of that? Remember, that is our original goal, right? Is this good? And why do we do this way, right? So that's a question that we should ask immediately. And of course, we can, if you're thinking about, have you ever wonder why the integral size always look like this? Right? Of course, Leibniz invented this size integral, right? But actually, it's have a meaningful s. It's like s, like sum, right? So if you're thinking about, this is how I look at it. When I look at the integral, it's a sum. So it's natural to see that, to yield this, approximate that, right? In fact, if you learn mathematics, right, Riemann integrations, you know, right? It's just, you can approximate integral, or you can look at Riemann integral as a Riemann sum and to the limit, right? So it's not surprise. For those who actually not really mathematical background, and I just want to say, right, this is a sum, so it's natural to do a sum here. But then 1 over n here, why, right? And why don't I have any weight, right? Why that I can do just sum them up like this? If you do Riemann integral, you know that there's actually some like delta x I or something as well, right? So here we don't see any delta at all. But in a sense, right? In the sense, it's a kind of delta here, right? Because when n go to infinity, right, this, right, is actually go to 0, right? Hopefully this actually converges to that. Okay, so it's actually, if you have a mathematical background, that's fine. But if you don't, that's also fine, right? But because it's just an approximation. Okay, but a couple of things. Our next question is that, where do I get this sample from? Xi, Gxi, where do I get it from? Right? And typically in practice, they are actually random. We actually pick them randomly, or they are randomly generated. Okay, so that's the practical situation. We don't have a deterministic way to, in most applications, these Xi and Gxi are random. Okay, together as a pair, as random. And as soon as you see random there, right, the right treatment for this kind of learning is statistical learning, right? Or we have to use probability to actually to have a proper understanding about this process, right? Going from here to here, and the conversion of, right, of this problem to that original problem, right? Because that's actually the ultimate problem, right? And you're going to see later, right? That's actually called the generalized general risk, okay, or generalization error. That's what they call a generalization error. If you do machine learning, people are talking about generalization, right? That's actually a generalization error, right? This is an empirical error, right, that we have. But in order to do that, right, the right language is probability. Okay, so I hope that I give you motivation. Okay, let me just one more emphasize on that. These xi's, right, and gxi are random, and they actually, you actually typically we call this, they come from a joint distributions, right? They are randomly draws, right, from some distributions that we don't know, right? So therefore, the correct or the proper way of learning machine learning is, at least from my point of view, is statistical learning, right? Machine learning, because we have to take into account the randomness, the uncertainty nature of our data, the limitation of our data. Okay, so that is the focus for the today and on Friday, right? We're gonna go through some probability theory, right, to prepare us to understand this better, right? And it turns out, right, it's just ahead of time. It turns out, right, by the law of large number. If you do statistics here, if you take some probability or Monte Carlo method before, law of large numbers, right? We know that this actually converges to that. If xi's, right, come from IID, right, samples from unknown distributions, then this actually converges to that almost surely, right? At least, right? At least that's what we can say. So that's just ahead. But in order to actually talk about that, we need to go through some, at least some elementary probability theory. And then we're talking about, of course, then we go back here, do an optimization again. But the optimization now is actually in the stochastic gradient descent, right? Because not only the data is actually random, right? And we're gonna do the usual machine learning do, right? We're gonna do a batch, right? We're not gonna do take on sample. We're not gonna take on n here. We just take a small batch randomly, right? And they're the name stochastic gradient descent. And we want to show that this actually converge, right, to the stochastic gradient descent. What does it converge? Under which condition does converge? And what does it depends on? What kind of error right? Randomness actually contribute into the stochastic gradient ascent. Understand that, right? Understanding that allow us you to actually in practice to use stochastic gradient descent more efficiently. Okay, so that's our goal. Let's see how we if we can achieve that. Any question before we start? Yes. Something that actually we don't know. You're going to see, right? So xi's and gxi together, right? We're gonna assume we actually we're not gonna assume typically that's what happened, right? But we on in the theory that we're gonna later we're gonna develop, they come as an IID, independent identically distributed from an unknown distribution. So this is another beauty of machine learning. We don't know G. We don't know the distribution. We only know a few samples. But the question is that can we still learn, right? Can we still learn? Can we still talk about the error? Can we talk about conversions? And it turns out that we can. It's just kind of amazing. The sample we know, but we don't know the distribution. Yeah. We only know, n samples. That all we know. We don't know distribution. That's what we assume. Yeah. Okay. Any other questions? No. If not, then we actually talking about today. We're gonna hopefully that's a little motivation for us to understand why we actually need to look at probability theory. Okay. Okay, let me deal with that later. So it's a very short, right? It's an introduction to probability. Okay, so and again, right, we're gonna try to do very constructive when we try to do, an easy way, right? If you open, by the way, so probability theory can be understood as a subset of measure theory, right? If you learn measure theory, that's actually can be considered the most general theory. So, but because the probability theories we restrict into the measure on with one, right? It's actually have additional thing that measure theory typically don't have. So if you want to make connection measure theory, this is kind of, you can understand probability theory is just a subset of measure theory, right? Integrations. So what we actually need to make sure that we understand thing a little bit, the definitions here, definitions, deterministic event. So what is a deterministic event? An event is called deterministic. By the way, let me actually do the deterministic if its outcome is completely known. Okay, so if we want to do just an example here, an example is that today is Tuesday, right? That's for sure. Tomorrow is Wednesday, right? So these are deterministic event because it's only true, right? When we only know that it's outcome, right, which is true here, right? So let's say a coin has tail and a tail and a head, right? For example. So so these right, and then of course maybe the most closely is a rolling. If you're rolling a die, if you're rolling a dice, if you're rolling a dice, rolling a die will give us a number less than or equal 6. Oh, I'm talking about the standard dice, right? With 6 faces, we fix the thing, right? So that's that deterministic events where you know thing for sure, right? Nothing that uncertain about these at all. So the definition random event. So we need to know the basic thing first to build on, right? An event is called random. An event is called random. If its outcome is not completely known, is not completely known. Okay, so let us give us a couple of example. So the example is so for example, rolling a dice. You don't know what the outcome is. It can be any face, right? It can be 1 or 2 or 3 or 5 or 6. When rolling a dice, for example, flipping a coins. Um, yeah, or the weather tomorrow, right? So the weather tomorrow, you don't know for sure. We don't know for sure. Okay, so these are random events because when it's interesting, right? Random. So we have an expert on Bayesian here, Professor Chung Hao. Whenever we don't know, right? Whenever we don't know, we assign as random. It's basically random as reflect our incomplete knowledge. Right? Thinking about this, random event is the event where we have no complete knowledge about it, right? So that's we human to assign as a random. Okay, so I think some of you do random variables, right? What is random variable, by the way? So we're talking about random event. Have you actually know what random variable means? Don't worry. That is actually what we're going to go through, right? To understand exactly what random variable is about. Okay, so that's the difference between deterministic and random events. So now we're going to do a little bit about probability space. Okay, so this is the important very important subject or objects in probability theory called probability space. Okay, so it have three important. This have three important objects within the probability space, right? The first one is called a sample space. So we call it omega, right? Omega is a sample space. Sample space. So a sample space, basically, you can think about, right, containing all possible outcome of, right, an elementary, let me put in quote here, an elementary event, um, event, typically we put the little omega, right? The little omega, little omega. Maybe give you an example, right? So that you can see a little bit better. Right, example here. So the elementary event, for example, elementary event, such as, flipping a coin, Okay, then the sample space is the following thing, right? The sample space is on possible outcome. So we have only two possible outcome, right? Of course, we're talking about a fair coin here, right? So either head or tail. It's either head or tail. There's nothing in between. So by the way, this is what I mean is that, I'm sorry, I have to make sure that you understand my notation here. When I write this, what I mean is this. I just write it so fast, right? It's just a curly parenthesis. That's actually what I mean. But I'm going to write it fast, right? So, and then of course this. This means this. It's an open one, and then this is actually a closed one, right? So it's actually curly parentheses, right? That typically they know by set, right? In mathematics, if you do set, you use curly parentheses. So when you see this, thing that I write, right? I mean this means this. Or if it's at the beginning, this means this. Okay, sorry for my handwriting. Okay, so another example, just to make sure that we understand, is actually if I look at the elementary event here now, rolling a dice. Rolling a dice, right? Then the sample space, and then omega is, as we know, right? It's either 1, 2, ... 6. You have only 6 phases, right? So it contains all the outcomes. It contains all the outcomes of the elementary events. Okay. All right. So now the next two subjects. Is it good? Any question on the sample space? Okay. The next object is the important one. The next object is the sigma algebra. Okay. So, but we're gonna go very quickly. So F. This is called sigma algebra. Okay, that's a mathematical way of calling, but for us, right? For us, we simply understand this, right? This is just measurable. Okay, so what do we mean measurable? You see that we're gonna see that the sigma algebra is cannot be defined by itself, right? It need to come with the next object, which is called the probability measure. We're gonna talk about in a second. We're gonna determine by measurable. 1 second, right? And on measurable events. On measurable events, A, that is a subset, right, of omega D's, a sample space. Here, measurable means measurable events is an event that can be assigned a probability. So you see that is not probability. The sigma algebra is just unmeasurable event. So this is just a mathematical way of saying thing, right? But for us, a set, right, that contain on subset of the sample space, contain on a subset of some sample space, right, for which each of subset we can assign a probability. So what do we mean so by assign a probability? So we have to go immediately to that, right? So we're gonna do D2 together. We're gonna do D2 together. We're gonna do B C. We need to the probability measures. C is a probability measure. P. So we're gonna try to do this, right? The P at the usual, but we have a double bar. The double bar on the left side of P is P, a probability measures, right? A probability measure. A probability measures is a map. Is a map. Okay, so we're gonna look at everything from mathematical point of view, right? So you see, basically set and function we are talking about right now, right? So F from mathematical point of view, right? Omega, you think like R, right? And then F sigma algebra, you can think right now just a a subset, a setup on subsets, right? But there one condition measurable. But for the sake of simplicity, just you think about F is just a subset on or setup on subsets, right? And then the probability measure, it's just a fancy name, but it's just a map, a function. It's a function, right? It's a mapped from omega, from the sample space to a very special interval 0 and 1, 0 and 1, to a very special interval and 1 to us, right? So P E from omega to 0 and 1. So it's a mathematical, right, function. That's it, right? Nothing special about that. It just have a special name. But for us, right, mathematically, it's just a map, right? So don't get concerned about probability, right? It's just a map. Okay, so but the conditions, right? Of course, P. P is special. We have a condition on P with P0. I'm sorry, not P0. P an empty set. P of an empty set. The probability of an empty set is conventionally defined as 0. And P, the probability of the whole set, naturally equal to 1, right? So probability that you are in that set, right? Thinking about flipping a coin. The probability that the face showing up is between 1 and 6 is for sure 1, right? Probably is 1. You cannot get out that, right? So probability that the face that's showing up on a dice is in the set from 0 to 6, right? From 1 to 6 is clear, 1. But of course, if you're flipping a dice, it must be between them, right? There's no like showing up nothing, right? So that's why the probability of the event of nothing, right, or phase doesn't have anything on there is 0. Thinking about the dice problem. Okay, so that is the conditions, right? It's a condition, and of course the second conditions is this, right? For any A in our sigma algebra, P of A is greater than 0, less than 1. Okay, so this is what we mean. We can assign a probability, right? We can assign a probability, right? So any set in our sigma algebra, we can assign the condition, right? To be in the sigma algebra is that you can assign a probability. Okay, so these two need to be together in the definition because they help understand one and another's. Okay, so two two elementary thing. I'm sorry, I should do not A and B here. I, double I. And then I have also two things here called the complementations, conditions, right? Is that if A is in the linear in the sigma algebra, then the complement is also in the sigma algebra. By the way, this is a complement, right? This is a complement, which is equal to omega minus A, right? That's a complement set. A prime is complement of A. Then another condition. So the sigma algebra, like I said to you, you can think it's just a set of all subset, but it's not quite right. First, it need to be on the set, need to be measurable. You can assign a probability, and I need to satisfy this condition, and it satisfy one more conditions, countable union. Now, what it means is that, right, if AI is in F for all, right, for all I from one dot 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 dot, right, then if you do a unions of all AI, I from one to infinity, this is also to need to be a subset of F. That's actually a condition, something more abstract, right? So it's in a sense, right? It's in a sense, if every set is measurable, if every set is measurable in here, then a union of them is also measurable. Okay, so that's in words what it means, right? If I have a collection of sets, each of which is measurable, each of which I can assign a probability, then I take a union of them, then that union must be measurable. That is, I can assign a probability. Okay, so that is the a condition for F or for sigma algebra. Okay, so for the sec, I said, right, if you, this is kind of natural condition. If you think about this natural condition, then you can boil down to a set of all subsets who you can, right, each of which you can assign a probability, right? And this is actually quite natural, right? If I can assign a probability to A, then I can assign a probability for the complement, right? So it's up to you how you wanna memorize it, right? But this is one of the thing that that you need to know. It's very easy, right? In a sense. Another condition for the probability that that we need to know is this: if on the AI in F I and then AI intersect with AJ is empty, so on disjoint, right? This is disjoint set. So they don't have anything in common. Or mutually exclusive event. This is also, called mutually pairwise disjoint. I'm sorry. This is, I think it should be pairwise disjoint. Should be or mutually disjoint. Mutually disjoint, or mutually exclusive event. So this is just the probability language, mathematical language, just mutually disjoint, right? But probability people typically have a different name, right? Or more intuitive name for it. You can think of that way. Then, if you have this mutually disjoint set, right? Then the one of the condition of the probability is that if you take a union, if you union upon this set I from 1, right, to n, then it is equal to the probability of each subset, and then you sum up 1 to n. And that's actually thinking about, actually, by the way, I would like you to think, right? Another thing that I really would like you to have in mind is this. The probability measure like an area. Think about area measure, right? An area, okay? So the area of the sum of different shape, and they don't share anything common, is equal to the total area. Something that way. Everybody see that? But E is equal to the area each shape, right? Summing up, right? If you have on set that don't share to each other, there's no intersection, and each shape has its own area, right, or volume, then the volume or the area of the union is equal to the sum of the area or volume of each subset. Everybody see that? So that is some intuition that I want you to have in mind. So probability, you can think about, it's a normalized area. Thinking about that, normalized. Normalized means that the area of the larger set is 1. The area of the smaller set is 0, or the volume, right? If you think that way, then this is going to help you, to understand probability theory or probability measure a little bit easier, right? Connect that you know. Okay. So let me actually do an example here, right? One more example, and then before we go to something more interesting. So example. Any question, by the way? Any questions? So elementary event again. Event mean here in this case is flipping the coin. A fair, right? Of course, a fair coin. Then we already know, right? We know a couple of things. Is head. I'm gonna do a lazy thing. Okay, H mean head, and then T tail. Okay, and then second, we know that the sigma algebra in this case, by the way, are all subsets. What are sigma algebra in this case? We're only talking about the sample space for flipping of coins. Can somebody list out the sigma algebra here for us? What is the simplest set in the sigma algebra? Just one. Yeah, sure. Just flipping the coin. We're not doing any random experiment here. It's just a flipping a coin event. We know either head or tail. What is sigma algebra here? Of course, the first one is empty, right? Of course, you never see that. So, of course, the empty set is always there, right? We always assume that is there. And then, of course, is head. And then, of course, tail. That's it, right? Everybody agree? Is that correct? No? So you said no. Why? Yes. That's correct, because by definition, omega is a subset of itself, right? And definitely it is measurable, because remember, P omega, the condition is that P omega is equal to 1. It's definitely measurable, because it's actually have 1, right? Probability 1. So that's very good. So that's actually all we have for the sigma algebra. And then third, okay, we're gonna do assign probability, right? Of course, it's natural to assign that the P of empty set is 0, like I said, and P of omega itself is 1. And it's also, right, it's also natural to conventionally agree that head, right, the probability of head is half. Now, if you're talking about experiment, right, turns out that, in the experiments, half of the time you get head, and then half of the time you get tail. So it's natural to assign the head, the probability of getting head, and the probability of getting tail is 1/2, right? Just by experiments. Good. Okay, so that is a seamless probability space, and of course, right? One of the proposition here is a seamless proposition. I want you to prove immediately, and we're not going to prove it, but it's easy, right? P A prime is equal to 1 minus P of A. Actually, maybe I should do it for you just for fun. So the probability of the complement is equal to 1 minus the probability of the original set. Very easy, but actually it's required us to apply a couple of not a couple, right? one single thing, right? So notice, actually, why don't we just, for those who actually haven't seen before, why don't we just do a proof for this easy thing, right? So notice that A intersect with A prime is equal to empty, and then A union with A prime is equal to omega, right? All right. So we know that the P of omega, so these are mutually disjoint set, right? A and A prime are mutually disjoint. P omega is nothing more than the P of the unions of A and A prime, right? Because that's by definition. But A and A prime is actually mutually disjoint. Therefore, by definitions, it's a sum of the area, right, or the volume is equal to the sum of the volume of each individual. And that's it, right? On the other hand, we know that P omega equal to 1. That's it. That's it, right? So PA plus PA prime is equal to 1. Actually, what I want you to prove, actually, I'm not going to do this. I'm going to ask you to do this. Propositions. Another proposition is that if A is a subset of a B, then the area, thinking about this, right? Like I said, it's just thinking about an area. If a set is a subset of another's, then the area is less than or equal. So want you to prove it. Okay, actually very simple proof, but it's a little bit trick. You can make a very long proof, but actually if you take a little trick, then it's actually much one line, just one line proof. Okay, so that's another thing. Actually, another important lemma is here that I want you to do. I think very simple definition, but there's a lot of result that we can do. And one of the most important rule is the called sum rule. Sum rule. So what the sum rule says is the following, is that, okay, so any A, B is, we look at a subset, right, of the sigma algebra, their holes that the probabilities of unions, this is two arbitrary set now, is equal to the probability of each individual shape or the area minus the area of the common of the intersections. And again, it's actually quite obvious, right? We have this when we learn geometry in middle school, area, right, or volume. The volume of the unions is the volume of individual minus the volume of the intersections, right? So that's actually not a surprise. How to prove it is actually very easy. A couple of lines, right? By a couple of tricks. It's in the lecture notes. Okay, it's in the lecture notes. But the key is this corollary. The corollary is super important, everybody. It's called a union bound. And if you do, um, statistics a lot, and it's actually machine learning. If you do really mathematical machine learning, right? One of the bound that you use again and again to prove many results, especially non-asymptotic or non-asymptotic statistics, which I do quite a lot with my research as well, is the union bound, right? The union bound is the simplest possible bound that you can think about, right? But it's actually one of the most useful. It's amazing, right? Is that if if you take 2A, regardless A, B, R, right, as a subset of our linear algebra, is there any way that we can control the air conditioner? Is that, can I move? Can I move away from the air conditioner? It's just like blow directly into my face. So if I can move, if I can sit on maybe there, maybe on that side, this side is okay, but that side it blow directly into my face, and then I'm cold now. Let's see whether I can move. Chung Hao, let me actually, I think I can move a little bit, maybe without interfere. Yeah, either, I know. What I mean is that we can either turn it off. I'm a little bit, I feel a little bit cold now. Okay, so I think it's good. So this is the union bound, right? So the area or the volume of the union, the name is actually very, very intuitive, right? Is equal to, I'm sorry, less than or equal to the area or the volume, the sum of the volume of each individual. Very, very easy to understand, right? Very easy. The proof of this one is actually obvious from the sum rule, right? If you can prove this, and this is actually not even one line, one word, going from here to here, right? Because remember that the probability of any set is always greater than or equal to 0, right? This is always greater than or equal to 0. That's it, enough to go from here to here. So this is union bound is actually one of the most important. Remember, right? Remember that if one the thing that you remember today, that is something that you remember, should remember, and it's the easiest one, right? Of course, it's generalized, right? Generalized in the sense that if you have AI belong to F, of course, right? Generalizations. If AI is subsets, measurable subset of F, then the area or the volume of the unions, I from 1 to n of AI is less than or equal to the sum of the area or the volume of each individual shape. So that are more just generalizations. But it's easy. Actually, let me actually apply. You see how beautiful the union bound is. I'm gonna show you an example. You see the beauty of the union bound. It looks so simple and it looks so intuitive. But when you, who's gonna use this, right? Who's gonna use this? Let me give you an example. And this example is very practical, okay? Very practical. A. Look at a couple of events. A is an event of conducting the class virtually. Actually, it's interesting, right? I was in Japan 2 weeks ago. I was there for 10 days in Taiwan. I think Taiwan wear more masks than Japan now, I think. I was there, not many people wearing masks. Of course, I'm from Texas, no mask at all. Like Texas is very wide, okay? So we didn't have masks for a long time already, right? But it's good. Having masks is actually protect ourselves, right? That's good, that's good, that's good. It's just like Asian culture is very natural. We have masks. I'm sorry, did I forgot the time? It's good. Chung Hao, you should have mentioned to you have to remind me. Okay, so how about this? Let's have about 10 minutes break, And then we come back to actually apply the union bound, right? It's very useful, super useful bound. So like where we left off, right? We are talking about an application of the union bound. It's see how it's in practice. And the reason I'm talking about math because actually our example related to like COVID type of thing, right? So conducting, so the event A, conducting the class virtually, and B, of course, conducting the class in person. Of attending, I'm sorry, this is attending. See, attending, different, they are different, not conducting. Why do we actually, why would it be silly to say B is an event actually conducting class in person? Why is that? Originally, what I wrote, it would be unnecessary to say so. Why is that? Instead of say attending, I say conducting the class in person. It would be unnecessary. Why? So this is where the theory and the practice, right? Because we have only two modes, in person and virtually. So they are complementary event. If I know A, I know A prime. So there's not necessarily to define a separate event for that, right? So see, this is where A and A prime is, right? So it's unnecessary to put conducting there, okay? Okay, so we also assume, so this is assume. Sorry. I'm going to assume that the probability of conducting class virtually is epsilon 1, right? So especially now, the probability that we have the class in virtual is very, very small. So that's 1. And then the probability of attending the class is actually epsilon 2. Okay, in person is 2. For example, you know, I didn't know actually. I just look at the window from my office. Actually, it's very dark outside. Yeah, I was surprised. I thought it was already in the evening, but it's raining and there's a lot of thunder outside. Okay, now we consider. Actually, this is one of the most my favorite example, right? Because it's so important to see the union bound in action. Consider the event. The event of C is A prime intersect with B prime. Right? So that is, right, this is attending the class. The class. I'm sorry, not in person, virtually as well. I'm sorry. One is attending and one is actually conducted virtually. That's right, virtually. I'm sorry, I actually, I miswrite because then otherwise it doesn't make much sense, right? So that also makes sense that, you know, at this period of time, attending the class virtually is quite, you know, small. Okay, so C would be, right, the intersection of these two complementary events would be attending the class in person, right? The class happen in person and you attend in person, intersections, right? That's C. Okay, so you attended the class in persons. Now, applying union bound. So basically, right, basically you ask yourself, right, you ask yourself, A is an event of conducting the class virtually, right? The probability is this, is actually small. And your probability of attending class in virtually is also small. The question is now, what is the probability that a person, let's say I'm a lecturer here, right? I just wonder what's the probability that you come here attending the class, right? Because if it's high, then I gonna come. If it's low, then I don't. It's no point to come here. If the probability that the student or the participants showing up is so little, right? So that's a question for me. Or if you want to ask yourself, okay, so we're gonna do. That means we are interested in computing a PC, right? The probability of C is equal to, of course, 1 minus P of C prime. Okay? My 1 minus P C prime, and therefore that's what we just showed, equal to 1 minus P of C prime is what? C prime is A intersect union with B, right? C is intersection of A prime, B prime, then C prime is A union of B. What is the law that I use? Just a little bit check on you. Set theory. What's the law that I use there? If C is right, C is A prime intersect with B prime, then C prime is equal to A union with B. What law is that? Huh? The Morgan law. That's correct. Morgan, right? So that's a De Morgan law. Very good. So we just use De Morgan. Then we have that. Okay. Now, by using the union bell, right? By the union bell, now we have this, right? Then this is actually greater than equal, which is a union bell. It's greater than equal to 1 minus of P of A minus P of B, right? And therefore, it is equal to 1 minus of epsilon 1 minus of epsilon 2, right? In conclusions, the probability that a student or a participant, right, attending the class in person is greater or equal to 1 minus epsilon 1 minus epsilon 2. So if I know that epsilon 1 and epsilon 2 is small, right, I know that the probability that you attending the class in person is high. So then it's worthwhile for me to make a trip to come here. Everybody see that? The union bound, remember that the union bound is less than equal. There's a minus sign become greater than equal. Okay, the only thing that I do quick here is that the union bound, right, without minus sign would be less than equal. But if you have minus sign, become greater than equal. Greater than equal. Okay, so that's just a symbol application of union bound. Another thing that actually important in probability, all right, is the condition distributions. But I think for the sake of time, we're gonna go through this quickly, okay? So I encourage you to read more in the lecture notes. Conditional probability. So this is actually if you do Bayesian statistics, or basically it happen everywhere. Conditional probability. This is a very useful thing because that's actually, we always operate conditionally on something, right? As you can see, I'm gonna do that in a second. The conditional probability of A, given the fact that B already, right, B has already happened. given the fact that this event already happened, is defined as the probability of A condition on the fact that B has already happened is equal to the probability of the intersections of A, B. And this is the basic of Bayesian's your statistic and Bayesian theorem, right? You can use this to prove the Bayes formula. The Bayes formula you can prove, right, using this Bayes formula. And this actually due to Kolmogorov, right? This is important, right? Kolmogorov is considered one of perhaps the founding father of the probability theory, right? He's the one actually who formalized probability in the mathematical sense, right? Sample space, sigma algebra, that's the thing that we do, that's thanks to Kolmogorov. Okay, so an example, actually maybe an example for us to understand is this, right? An example is this. A. Okay, we consider rolling a dice. We're going to consider rolling a dice. And then A is the event of getting phase 6. Phase 6, and B is the event of getting phase greater than 4, right? That's the event greater than getting phase 6, and B is the event of getting a phase greater than 4. Okay, then you see, right? Assume that they assume, right? Assume that the dice is fair. Our dice, the dice is fair. So that means P of 1 equal to ... is equal to P of 6 is equal to 1, 6. Okay, then PB is the event of getting phase greater than 4, right? Then B is nothing more than the union of 5 and 6. Everybody see that? Right? Phase greater than 4 is 5 and 6. Two choices, right? It's a union of these, and we know that they are mutually exclusive, right? Then therefore it's equal to P5 plus P6. So it could equal to 2, 6. Okay? So we also know that PA is 1, 6. And then we also know that the probability of the intersections A and B, okay, is equal to is 6, right? A and B union is 6. It is equal to 1, 6 as well, right? Because A is a subset of B. A is a subset of B, right? A proper subset of B. So therefore, the probability of getting phase 6, right? Given the fact that we know that the phase is only either 5 or 6. Given the fact that we already know that B is already happened. B is already happened, that we know that either 5 or 6, right? Because B is greater than 4. So when B happens already, we know that it's either 5 or 6. The question is that what's the probability that you get 6, right? Okay, if we actually use the Kolmogorov, then this is A intersect with B. And this is P of B, right? We just plug in the formula. This is 1/6 over what is that? 2/6. It's equal to 1/2. It's also actually obvious, right? Why? Because if B is already happened, that means you have either 5 or 6. So the probability we can get in phase 6, given the fact that we know that the phase either 5 and 6 is 1/2, right? So it's not a surprise. It's not a surprise, right? It's not a surprise. So, but it's actually it's intuitive, right? It's quite intuitive, right? That way. And so it's at least the formula that Kolmogorov put down is meaningful, right? You can understand. I'm sorry. You can understand is that now originally there's no condition, right? When you say a probability, you look at over the whole space, right? For example, what is the probability to get in phase 6? The whole space is 1, 2, 3, 4, 5, 6, right? So the probability of A is actually 1/6 because you look over whole space. Now B is already happened. So you limit your probability space or sample space into only 5 and 6. Okay, so another way to think about the conditional probability is to limit you into a smaller, right, sample space. In this case, 5 and 6. And the probability of 5 within the sample space 5 and 6, right? Then it's 1/2, right? You can either 5 or 6. That's another way to think about it. Okay. Or any questions? This is very important, everybody. Actually, that's what we do, because you always make decisions in our life, always conditional on the outside world. Condition on the traffic. Should I go to school? Condition on traffic. Should I take this path or the other path to NTU, right? Condition on my financial condition, on my situation. Should I buy a house? Conditioning on based on what the class so far last week, right? Should I actually move here and stay here and take the class, or I communicate every day? Communicating on condition on financial support from my university. Should I come here every day? Conditional on my health. Should I travel every day? Right? You see that we make decision every day based on conditional probability, right? So if you're thinking about what is the most useful probability, right? This conditional probability, right? So when you condition, you limit your space of sample space. That's important. And you should look into that sample space. So don't get confused with the original space. Okay? That's what I want you to have in mind. Okay. So we talking about IID sample a lot. We're gonna all right. We will. So it's important to talk about independent event. So this is the first time we talk about independent event. So A and B, A, B, A is B in a sub in two set in the sigma algebra are called independent. Are called independent. If the probability of A intersect intersect with B is equal to PA multiplied by PB if they are independent. Okay, this is definition of independent. In fact, independence is very deep. If you really take the probability class, independent is one more deeper than we can think of. Okay, it's a deeper than we can think of. Actually, I put a few examples in here that I think you should take a look at the independence events. So right now we should understand this, right? Independence, it sounds like, right? You can think about this. I mean, at least right now, but it's not quite true. It's not quite true. It sounds like the area, right? the sound like the area of the intersection of the two sets is the product of the area of two sets, right? Think about our area or volume. But that's actually, this is where we shouldn't do the area thing. This is one of the place. Independence is actually a little bit more is actually a little bit deeper than what it should be, right? So an if, right? If we think about, right, if we look at the conditional formula, conditional probability formula, we have that P for two independent event, for two independent event. P, remember that A given B don't really happen, is P of A intersect with B over PB, right? But this is on the other hand equal to PA, right? Because they are independent by definitions. On this side, I apply conditional probability. On this side, I apply definitions of independence, right? So we conclude that if the two events are independent, then PA is equal to, or PA, actually this is the correct way to write it, PA given B is actually PA. So you see, right, it's basically what it says, that regardless, right, whether B happen or not, right? Okay, actually, let's say whether B happen or not. Okay, whether B happens or not, right, does not affect A, right? So now we actually no longer independent, right? So previously, before I came here, whether I go anywhere does not matter to you. What happened to you? Think about, right? Me, B is event of me doing something in Texas, right? Is actually independent of what you're doing here, right? Before I came here, of course, right? But now, thing happened to me can, you know, the probability that you do something, if you take this class, right, may not be completely independent on what I happen to me, right? If I'm sick, right, then you actually will not go to class, right? So we are no longer independent. But what happened to me before and what happened to you before, completely independent, right? Regardless of what happened to me, you just do the usual thing that you do. This is how we understand. One way to understand the independent is that, think about conditional probability, right? So whether this happen or not, right, it does not affect you, or this actually does not shrink, right? Does not shrink the probability of sample space. It does not, right? Because it's independence. They are not. It has nothing to do with A at all. Okay. Okay, so the next theorem is really important, right? That we use a lot is the law of total. The law of total probability. Law of total probability. So we're gonna let omega is equal to the unions of AI I from 1 to n. Okay? And we also assume that AI and AJ are mutually disjoint. It's mutually disjoint for all ij, all I that is not the same at j. Then, then for any, then for any, and for any event B that is actually in the sigma algebra we have the following. P, the probability of B is equal to the summations of the probability of individual event AI multiplied by the probability of B, given that AI is already happened. This is I from 1 to n. Okay? Actually, this is very similar to what you learn. There's one, when you learn integrations, right? When you do Riemann integrations, you actually seen this before. See, this is another thing, everybody, you know, especially I'm like you, right? We are student of something. Making connection with what you know is really important, right? So this actually formula is not completely strange or unfamiliar if you actually really understand the Riemann integration, right? And one of the Riemann or Lebesgue, actually the correct one is more Lebesgue integration, right? Is on Fubini theorem, right? Or iterative integration, right? Instead of taking the volume integration or the area integration is equal to the integral of two one-dimensional integrations, right? This is actually iterative integrations, right? The area of the whole thing, right? The area of the whole thing is actually can be broken into pieces, right? So you see that this is the probability that AI is already, this is the AI, right? This is probably B actually when AI is already happens, right? And it's actually it's not completely difficult here at all, because this is nothing more than by the conditional probability, right? It is equal to P of what? B intersect with AI. You see that? This is nothing more than the probability of B intersect with AI using the conditional probability, right? This time, this is nothing more than P of A intersect with B, right? So it's actually, this is integration P by P's, right? P by P together, you add them up. So this is a P of B intersect with AI, right? And this is actually where the area actually now become useful interpretations, because basically you chop B into little p's, right? Each of them with each AI. Remember that AI are mutually disjoint; they don't share, right? So the area, the total area, is the area of B on each of the p's, right? So thinking about, you make a cake, right? You make a cake. You put a raisin on each piece of the cake, right? The total raisins is the raisins, right? Is in each individual piece of cake or pizza, right? Pizza is actually one of the, right? If you had, 10 pieces of meat, right? And you put on, 6 pieces of pizza, right? The total of meat is no is the same as, the meat on each pizza adding up, right? This is what it is, right? If you're thinking about, the area, if I do the area integration up here, right? This double integration is nothing more than, if I take one stripe like this, right? If I want to take the integral of f of x and y, right? dx dy. I can do this. I can do, okay, f of xy, right? Dy right? F x y dy, and then I do in x after that, right? Or I can do the other way around, or I can do this f of x y dx, and then I sum up dy, right? So this is actually what it is here. If you look at this integration of the x, right? This is x and y. I'm sorry, by the way. So you say I'm chopping thing into pieces. I chop into pieces. This is x and y. So f is in like density, right? So this little here. If this is one, by the way, if the one is best, if think about this is one, right? The integral of the x here, this is the x here, right? From here to here. This is nothing more than the area of that little strip. This is the area of that little strip. And you add up all of the strip together, right? And that's the total area. Everybody see that? This is the area or the weight or the volume of this little piece strip, dy. And you sum up all of them. This is say that, okay, you calculate each piece, and then you sum up, you get the whole thing. Same thing of add out there. This is the same. Okay, you chop your thing into pieces, and then you add them up. So it's the more generic, right? This is iterative integration if you do elementary integration, but it's actually also Fubini theorem, right? If you do Lebesgue integrations. Anyway, it's just a little bit of connections. That's how I make connection between math and different field, right? Always try to make connections whenever you can. Okay, so that is, and the proof is actually inside the note as well. I want you to take a look. But actually, let me actually do an example here, right? You see the important, and actually it's very suitable for today as well, right? Is the probability and then the next thing we're going to do is actually the probability of class occur, our class occur. I didn't check the weather today, by the way. I didn't check. It looked so hot and sunny when I left the hotel. So it's perfect. The example, I did the example without knowing that today is rainy, okay? So the probability of class occur, given the fact that it's rainy, right? Given the fact that it's already rainy is a 3/5 P that the class occur, given the fact it's sunny, given that, the weather is sunny, is 99/100. Also with high probability, right? We have a class. But when it's rainy, a little bit harder to move, right? So wet. Okay, and then I'm actually I also assume that the probability that it rain, right? Rainy or rain is equal to 1/10. Right? Is 1/10. Okay. Well, then what is the probability? Of course, P sunny automatically, right? We assume that there's only two. This is the beauty of in Asia, right? Especially do we have snow here? No. Okay, so then good. So then I can do this, right? Either rainy or sunny. So 9/10. So makes sense, at least in Taiwan, right? So they are complementary of each other's. Okay, thus, right? With thus the probability of class occur. Okay, so this is actually so important, right? I mean, did you think that's useful? Because of given all the conditions. Okay, so this is conditions about outside, right? Rain or this is we based on the weather forecast. But this is depend on us, right? If it's rain, or the class, right? Raining, class is small. If it's sunny, then the class actually happen much higher probability. What we are interested in, or you, right, or as a participant of this class or student of this class, what is the probability this class occur? Because I want to make decision whether I should go to the class or not, right? If the probability that the class occur is so small, then I shouldn't go, okay? Because this is completely out of your control. All of these class occur or not depends on me, right? Based on whether I feel good about rainy or sunny. So you want to know whether you should go to the class because depend on me and depend on the weather. Okay, then you do this calculations, right? Then you do these calculations. Then using the law of total probability, right? This is equal to the probability the class occur given that it's rain time the probability of rainy day plus the probability of class occur even it's sunny. By the way, I mean, we finished this example and then we done, right? For the second, and then we have another break. Rainy is sunny, right? Remember that it's important to know that rainy and sunny are mutually disjoint. Then we can apply. See that? So this is easy, right? You can then do plug in the calculation 3/5 times 110 plus 99. By the way, I can spend weeks to teach you about probabilities. Probability theory is beautiful, beautiful. There's so many things that I want to show you, right? And my intuition I want to share with you, but yeah, the time is limited, so we have to move maybe a little bit faster. Okay, so simple calculations show us that the probability that the class gonna occur is more than 90%. Good, then you should go to class after you this calculation, right? A very simple and effective way of using total probabilities because this is what our life face every day. We make decisions under uncertainty. Okay, any questions? Okay, so I think let's actually take a break. So we came back at we started at 3:12 or so, right? So it's not quite 50 minutes yet. Okay, let actually do one definition and a half break. And this is actually important, right? The next subject is really important. Of course, everything is important. Otherwise, I would not spend time talking to you. But this is just like a little epsilon of probability now. But I think the next one is random variables. So this is really important. We're talking about random measurable. I'm sorry, random variable on the time. But this is what you should understand what random variable means, which is what I'm going to show you now, and what I want you to have in mind, right? After this class. Okay, measurable map first. M is from omega to S is called measurable. A map, a function is called measurable. A function is called measurable, right? If the inverse image, of any measurable set. Remember that the measurable set is a set whose, right, on which we can assign a probability, okay? If the inverse image of any measurable set in S, right, through, this is important, through M to the map or to the functions is a measurable set. Measurable set in omega. Okay. Let's plot it. Let's plot it. So we have two space now, right? We have omega and we have S here. Okay, so I'm looking at a set who I can assign a probability in here. Okay. Let me call that set A. And of course, we assume that our map is our function. This is M from omega into S, right? The inverse image. You see the inverse. That means M inverse of A. Let's say it is B. Okay. So so M, right? M is measurable if A is if two things, right? If two things happens. First, if A is measurable to N and B, which is the inverse image of A, immeasurable. Right? If these two conditions happen, then A is measurable, right? By the way, does it sound familiar to something that you learned before? Actually, very similar to something you learned before. That's correct. And this is actually a topology way of do definition of continuous functions. Okay, a continuous functions, if the inverse image of any open set is an open set. Okay, that's definition, topological definition of the continuity function, right? Different than the standard, that calculus way of definition of the much more general, right? Actually, the most general definition of a continuous function is the inverse image of any open set is also an open set. The measurable set is very similar to continuous, right? The only is actually you replace open set with measurable set. Very good. Very good. So, yes, it's a good time for us to take a break. And then after the break, we're going to do a random variable, right? What it means mathematically, what it means, random variables, right? It's not something abstract. It's something very. Okay, so let us start our class again. By the way, this is a natural way. Sorry, this is, if you think probability is difficult, right? The reason is that your most probability class is difficult because if the lecturer doesn't actually inject intuitions, right, and make connection. So, by the way, it's important, right? When you learn something, always make connection. That's how you actually, our brain works. The reason, it's like transfer learning. If you do machine learning, that's actually the fastest way to learn is to do transfer learning, right? So making connection is like transfer learning because I know integration theory. When I see this, oh, it's connecting with, iterative or Fubini, right? Then it's gonna get into my mind much easier. I remember it easier and it's faster for me to remember, okay? So try to make intuitions, try to actually make connections or do transfer learning whenever you can. You learn much more efficient, right? Based on my experience. And this is another way to do transfer learning again, right? So so you see that I start with sets, right? I start with sets. And then what I'm gonna do now is basically function, right? It's actually very natural. If you actually, if you're thinking about make connection, how you learn mathematics, and that's how mathematician does. Actually, you are a mathematician. I'm not. I'm a fake mathematician. I'm an engineer. I just do a lot of mathematics, right? But I'm not training, right? As a mathematician, I did took all graduate class in mathematics later when I finished my PhD. I took all math class, right? But I'm not really officially trained. But that's actually an advantage for me because I came to the class very well motivated, what I should learn and how I connect with application and intuition, right? Anyway, just a joke. But if you think about what we do here, it's a very natural mathematician does. What you do, right? And what you do when you have a Legos. Is it Legos are popular here in Taiwan, right? Lego is actually think about all piece together. It's like elementary events, right? A set of only little pieces. And as a human, what you do first? You transform them. You combine pieces into shape. You actually do a function evaluation. You do a transfer, right? You map thing into something else, right? So you actually buy a kit or us, right, putting Lego pieces together, we actually do a function mapping, right? So that's what we do. That's that in practice, right? You transform into a shape of a humans or a car. You do it, right? If you actually, mathematician, you should actually make that connection. What I'm doing here, actually, I do a mathematical transformations, a mapping, right? I mean, that's how you see mathematics beautiful. Otherwise, this has nothing to do with math. What is useful about mathematics? What about useful function? You learn function all along from elementary school, right? Middle school, but that's what you do all the time in your practice every day, right? You have different ingredients. China is famous for what? One of the most famous thing about China is cooking. You have ingredients, different ingredients. Think about omega is a set of all ingredients, right? You do transformation, you do mapping, you do apply functional mathematical mapping into different type of dish. Do mapping. On the cook, I do mapping. Function, right? That's what they do. Mathematician, what do they do? You have a set, and you are tired of do set theory. The next thing you do mapping. Very natural way of mathematician way of doing things, right? So it's very natural for us to talk about next thing is mapping because that's what we do. One we know the set, we know the operation on set. The next thing we do is move things around, combining things, and see how it look, right? Okay, so a little bit of connections. So if you try to make connection all the time, you see mathematics or probability or any science actually beautiful. Okay, so the next object that we're going to do is a random variable. Okay, and this is actually by far the most important definitions. Random variable because that's what we do in practice. Okay, so what is a random variable? Random variables, it sounds like an abstract thing, but it's not. A random variables is a measurable map from omega to S. S typically we call it state, right? State space. The original space we know already is sample space, but this is space. Okay, so so it's actually it's very simple, right? A random variable is a map from a sample space to space. And we, by the way, we just for simplicity, we assume onto, right, or subjective. It doesn't matter. If it's not subjective, then we just limit into a range, right? A range of the functions. Then it's still subjective, right? Or on to. Okay, so if you give me an omega, I'm gonna return you an m omega that is in S. Okay, so random variable is actually very simple, right? It's mathematically, right? That's what it is. It's just a random variable. It's a map or function. That's it. Nothing more, nothing less, but a measurable function, of course, right? Nothing more, nothing less. Okay. So the next important thing is this, right? Is the next important thing that we want to do is actually a push forward, right? A push forward measure. That's actually the important thing. This is typically where the probability the theory is different than the traditional math, right? Because not only right, not only remember that on the original space we have on the original sample space, right? We have sigma algebra. You have a probability measure there that we already have, right? But the functions now also new. The random variable is a function that takes our sample space into a state space. The question, of course, it map set to set, right? That's what we clear. And it's also map the whole set into S by assumption, subjectivity, or onto. It map the whole set into the whole set. But how about the probabilities? In a sense, it's also map the sigma algebra to a sigma algebra. Right? Remember that it's an inverse image of any measurable set is a measurable, right? Because the inverse image is actually in sigma algebra, right? So it's actually map sigma algebra into a sigma algebra. Okay, it's map a set into a set. It maps sigma algebra into an algebra, sigma algebra. The last question that we're going to ask, how about what does it do with the probability, right? Does it actually map the probability measure as well, right? So that's actually a natural question for us to ask. And this is exactly what the push forward measure means that we're going to introduce next, right? Recall that if m is a random variables, and typically the people separate random variable means the value is actually real. It's actually scalar. I'm sorry. Then random vectors, right, is multi-component, right? The output is actually vector value function is random vector, right? A random variable typically, they conventionally typically, or not universal, but many actually consider random variable as actually a scalar value function, okay? Or mapping, measurable mapping. If M is randomly measurable and A belong to S measurable, then B, which is the inverse image of A, is measurable. Okay, so the question is that, right? The question is the question is if we assign a probability to A namely PA, what is the probability of B? I'm sorry, B, right? What is the probability of A? Okay, so remember that we have this figure. Let me copy and paste it down here. Okay, give me 1 second. Give me 1 second, and I come back down there. I'm lazy. I'm gonna copy and paste now. Okay, because B is a measurable set in omega, right? Because B is a measurable set in omega. So we know what PB is, or we can assign. We know that set B have a probability by definition, measurable, right? The question is, what is PA? How do we define PA, right? Given the fact that we know PB, because that's by definition of the sample space, right? So what is PA, right? And that's actually a natural thing, right? This is a push forward measure. This is definitions. And then the natural answer is what? What do you think about what should we define P of A? Probability measures. Okay, so we typically, there are many notations, but this is one of the notation. Mu of M, the probability measure of M on the set A is sometimes written as M, the power sign, and then P, okay, of A, is defined as the probability of B, or the probability of the inverse image of A, any set. And actually, this is actually meaningful, right? It's actually very natural for us to define this way, because M map B to A onto A, right? Then whatever the probability that B happens, then the probability that's the C the same as the probability that A happens, right? Because essentially they are the same, right? The probability happened here, that this set happened, should be the same as the probability this A happened. Very natural. This is exactly what we wrote here, right? The probability, right, generated by M. So this is, you think about, this is generated by M, or M as a map push forward the measure, right? You have a measure originally on the sample space. Now M push forward that measure into the probability measure in the state space. That's why the name. By the way, the name is not mine. I make up the name. This is a name is a popular. It's actually quite conventional, right? In probability theory. Actually, everybody use that. If you look at any book, that's what it is, right? So this is another way to actually denote that, oh, this measure is not by itself. It's actually a push forward, right? You push the forward of P through M, right? From the sample space to the state space. So therefore, it's meaningful to say that the probability that A happens is the same that the probability that B happens, or the inverse image of A, right, in general. Everybody see that? Very natural way to define. So nothing actually mysterious here. Very natural way to define. Definitions, okay? The question for you is that, actually, I'm going to ask you to do this, right? Show that. Actually, one of the homework here, I'm going to ask you to show that mu M is indeed a probability measure, right? By satisfying all the conditions that we talked last time, right? At least 3 conditions. Given the fact that P is a probability measure, right? Show that mu M is a probability measure. In particular, you have to show what? You show at least a few conditions that let me wrote here. Okay. show that actually at least three condition here, right? Actually, no, not only three, it's actually more. Actually, yeah, three, yeah. So show that this, actually now the empty set is actually not on the state space, right? What is the inverse image of an empty set? Empty. So the probability of an empty set there is equal to the probability of its inverse image, which is empty, therefore zero. So it's easy to check. Inverse image of the whole state space, because we assume that subjectivity is, right, is the same as probability of its inverse image, which is the whole omega, which is also one. So these two, I actually have proved two things for you already, right? You verify the rest, and that's how you learn, right? Just verify it by yourself. Always, never scare writing, right? Writing is how you learn. If you do mental arithmetic, that's not how you learn, okay? You learn much better if you write out everything, especially knowledge, right? It's important. Okay, but everybody show it, and then you actually understand it better, right? If you don't show it, you will not understand. Okay, so that's our definitions, right? That's our definitions. So typically, right, we also write, right? We also write, or we also write. We also write, right? Mu, the probability measure of A, because it is equal to the probability of the B, which is the inverse image, right? This is the inverse image of A, right? Or it is equal to the probability of, I just rewrote it, right? This is, sometimes we also write this as an integration, by the way, right? We do integration of P of D omega. And this is actually a very intuitive, again, if you learn a Riemann integral or Lebesgue integral, right? So think about this is P, is an area, right? So this is nothing more than the area of the whole set, B. What is it? You see the sum of all the area, little area, compose B, right? So this is the area of a little incremental or tiny piece, right? In B, you sum them up, that's the total area, okay? So that's actually typically what we do, what people write as well. P, the probability of a small, little, tiny event. Okay. Now this is where we introduce the probability density, but it's actually too difficult, right? You see that? Whenever I want to calculate the probability in the state space, I have to pull it backward, right? I have to pull it backward to the sample space, and then measures the probability of the inverse image in order for me to tell what is the probability of my set in my state space. Everybody see that? That by definitions. And this is where, and this is how you understand the density, probability density. What is the probability density, by the way, right? What is it? Of course, I only answer you what is a random variable means already, right? Easy. Now, what is a probability density? And probability density, right? The main motivation, at least how I see it, right, is actually to overcome this challenge or this cumbersome pull backward and then push forward, right? So the probability density actually allow us to actually eliminate the step going backward. Okay, so this is where we define probability density. Okay, so the probability density, what is it? It's easy. Well, we're gonna define, right? Pi of m, a little m, or for simplicity, we should do pi m where M is a random variables and M is a particular values or outcome of M. So this is quite conventionally people use a lot in probability theory, or you use capital for the random variables. But when you're talking about its value for particular values, right, or its outcome, you use the lowercase. Is called the probability density. Okay, of a random variable. Random variable M. If, okay, so pi M is called a probability density of a random variable, capital M, if you want to measure the probability of a set A in the state space, instead of pulling backward in the sample space, if you can somehow magically find a function, then you can use that function to operate directly on the state space, right? That helps you to calculate the probability of A without going to the sample space, right? That object that I just put there called probability density. Okay, so that's that definition of probability density, very, very intuitive. It's not something abstract or not something. It just help us to circumvent the situation going back into the sample space to calculate. Okay. So that is the for example, actually give us an example here, right? Of course, you know a lot about Gaussians, right? Of course, I give you one example here, right? A couple examples, perhaps. M is a uniform random variables on AB. And it's called uniform random variables. Anyway, if the probability functions is given as pi M is equal to 1 over B minus A, right? So this is mu M. So therefore, right, if you want to measure, probability of any set A, this is by definition, right, the integral over A of pi M dm is equal to 1 over B minus A dm A. Okay, so and typically, of course, this is for all A that is a subset of AB, and we write, many people write, not everybody write this. M, right, is distributed. M is a uniform distribution between A and B. U, A and B. Okay, another example. And by the way, you see that, right? If you learn the Riemann integration or Lebesgue integration, this is just nothing more than actually this, right? is the density. Actually, by the way, I'm sorry, I shouldn't say this. I should have say what dm means, right? Dm means it's just the usual, right? Dm just usual. Usual. I'm sorry for those who haven't seen. If you even haven't seen Riemann integration, right? Now I throw you another word, Lebesgue measures, right? Don't worry about that. I just want to be hopefully inviting you to take more math class. But this just think about this is the length length measure of our case. Think about that, right? In fact, length is a particular case of Lebesgue measure. But for the purpose of you to understand, if you haven't seen what Riemann integration or Lebesgue integration theory, don't worry, right? It is just the length for this particular case. Yes. More? Right here? Okay. A random variable, yes. You don't need to actually, you see the way to you don't need to define the probability, say, for both. You just need to buy, especially you only need to define the probability on space on the domain is enough. They're gonna be random on a map on the push forward everything to the state space. Mm-hmm. Yeah, sure. Sure. DM, yeah. Actually, I should have said this, right? I'm sorry. I should have said this. That actually I put down here. Actually, that's a very good question. I forgot to mention that, right? I put it down here, but I forgot to mention that. So DM is just for us, right? For us, DM now just the Lebesgue measure, okay? Or area. Think about volume measure. But I say volume or area or length measures. Or if you want to do more, mathematically, Lebesgue measure, standard Lebesgue measure. Okay. Yeah. This actually just yeah, it's not real. Like I mentioned, it's real. Yeah. Or RN. Yeah, in general. Actually, yeah. No, wait. Actually, M is not original, right? This is not original. This is not a measure. By the way, I'm sorry, that's actually also a good question, right? DM is a measure on here, Lebesgue measure on here, not on here. Okay, not on here. That's need to be distinguished. They are different. Okay, that's first. So we don't push forward the Lebesgue measure here. Yeah, that's right. And this is a relationship between the push forward measure and the Lebesgue measure in the state space. That's correct. probability density. Yeah, that's right. That's right. That's good. That's good. That's good. Yeah. So, but by the way, it's not to be. This is actually not limited to Lebesgue measure also, right? Right now, just do Lebesgue measure for us to understand, but it's not limit. Actually, it can do infinite function space as well, right? Everything here we go through this now. This can be a function space, right? S can be a function space, not only Euclidean space or any space, right? So that's good, right? So pi here, right? Pi here is actually the density of the push-forward measure with respect to the Lebesgue measures, right? Or if you want, again, I probably to invite you a little bit to learn the radon-Nicodim derivative of this one with respect to this one is actually is pi, right? If you want to interested in a little bit, the radon-Nicodim derivative is actually a much more general definition than the standard derivative that you learned so far. In fact, you can show that the standard derivative is a special case of radon-Nicodim derivative, right? And which is just we need at least 2 semesters to go through everything in theory and with the rigor, right? But hopefully I throw at you not to scare you, but to give you much more than what we have here, right? That you can learn. But yes, you're right. This is the density of the put forward measure with respect to the Lebesgue measure in the state space. Why don't we just write that? Okay. Why don't we just write that? How about this? This is the beauty, right? If you have an iPad or a tablet, this is a beauty. If you do a traditional person, then you cannot do this, but I can do it. Okay, so now we can actually sneak in what we just said. Okay, so therefore this is implied that pi, right, is a probability density. Is probability density is the density of the push forward measure mu m with respect to the Lebesgue measures in the state space. And you see that we completely remove the sample space. We don't want to refer to sample space. It's complicated, right? To pull back and work there. So we work directly with the sample state space. Okay, and this actually is also right. We also write d mu m dm is equal to pi m. Okay, and this is a radon Nicodim derivative. Sorry. I forgot now how Nicodim. I think it's Ni Nicodim derivative, and it's a special. And it's a much more general. You can show that the standard derivative, the derivative that you learned so far, is a special case of the radon Nicodim derivative. In fact, it's actually quite easy to understand, right? Because thinking about this. Actually, this is again transfer learning. This is where you do transfer learning. So this is nothing more than this is the antiderivative, right? This is the derivative. The integration of the derivative is the antiderivative, right? F is equal to integral, fundamental theorem of calculus. F of x is equal to integral of f prime y dy. This is what it is here. So this is the antiderivative of this with respect to dx here, right? If I put out dx here, if I put this is f prime, then this is f. And it's actually what we've seen before, how we define, right? Antiderivative and the derivative, right? So this is the derivative of this with respect to this. Transfer learning. So this is exactly what we've seen in the fundamental theorem of calculus. This is equal to the derivative of that with respect to this. So it's not surprised, right? It just have different name, right? So related to the fundamental theorem of calculus, you see that it's actually not surprised that Radon Nicodemus came up with this definition of, we call this a derivative. It's not just for fun, right? Just a direct generalization of the fundamental theorem of calculus. Again, try to do that, right? Try to make connection. Then you think, and then this is much more beautiful to learn. Okay, so let us continue. Okay, the next thing is actually expectation, the next important subject. So we understand what expectation, probability means, what probability density means, right? The motivations and the relationship with what we learned before. The next thing is expectations, right? The next important definition, expectation. That definitions, mean, sometimes we call mean, sometimes we call average, sometimes we call the most popular, right, is expectation. Okay, so the expectation of the expectations of M is defined as E with double bar, right? E with double bar. Expectation of a random variables is defined as, if of course we assume that random variable is this, is M mu of M dm. Remember that mu of M is the probability measure, right? Push forward of M in the state space. Now that's actually the most general formulations, right? These are more general formulations. But if we have a probability density, then we can do this, right? If when pi exists, then we actually have a more specific definition of expectations. Okay, but if it not exists, then the original what I wrote there is much more general. Okay. All right. So by the way, for discrete random variable, for discrete random variables, now it's important for us to make connection with for discrete. So far, discrete means that the values of discrete mean what? Discrete mean that the values of M omega. Remember that M take from the state space to this the sample space to the state space. The value of S is have a finite number. If M has a finite, when M omega has finite number of values. Actually, maybe I'll give you an example here as well, right? Example, right? For example, rolling, right? Rolling two dice, and M is the sum of faces. So rolling two dice. Each time you roll, you sum up whatever you seen there, right? I think that is one of the popular game, right? In casino, is that correct? Roll die, you add up, and then if you are above something, you get some money. If you, I don't play, but I saw something like that, right? So either sum of face. So then M, of course, right? M has only a finite number of values, right? Is it either two or 3, 4, 5, to what is the maximum? 12. Agree? So M has a finite number. So this random variable has a finite. You see the map is a map, right? Random variable is a map. Set only because it map what you've seen on elementary events. It map out omega into the state space. So you have only a finite number of values. Is that correct? Did I make any mistake here? Hopefully not. Okay. So just an example here, right? To show you. For discrete random variables, then the expectations of M is actually now defined as, right? Remember, it's very natural, right? That's an integral when things are continuous, but things are discrete. You replace the integral with a sum. M, I, probability of M equal to Mi. I from 1 to whatever, right? I from 1 to whatever number, total number of values of M. So this is a discrete way to define the expectations. Expectation is on basically all another one on average, right? Expectation means on average. What is the events? What is the outcomes? For example, right? For example, if I take an example and then we will see better expectations. A couple of examples, right? The couple examples. So let's take the uniform, right? M is uniform random variables on AB, right? Then the expectations of M, by definition, is an integral of M, right? Of M of mu M dm. But we already know that this random variable has a density. The density is B minus A dm A B. Okay, by the way, I'm sorry, I should have do this. This is a Hom S. This is Hom S, the integral over Hom state space. Okay, so this is Hom state space. In our case, the Hom state space is actually A and B. Okay, so this, if you put it out, so this is B, I'm sorry, this is 1/2 B minus A M square, right? AB. So what you get is actually B minus A, so B plus A over 2. Nice. Actually, it's also, right? It's also actually meaningful. Do you see that? It's meaningful to think about it because this is uniform random variables. The probability to get anything between A and B is the same, right? So on expectation, on average, we should the values of M is something in the middle, right? Okay, so that's an average. You think about, right? That's an average on expectations. What is the values of M? Okay, So another example, that's a continuous example. Let us do a discrete example. I'm gonna roll a dice. Okay, M, and now M is the number of the face showing up. Okay. So the expectations of M, right? So therefore we see that M have only on possibility 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. Because when you see a face, it can be only 1 to 2 or 3 or 5 or 4 or 5 or 6, right? So the value of M in this case is actually between 1 and 6. So the expectation of M is the summations of Mi, probability of M equal to Mi. Okay? And I is from 1 to 6. And this is summations of what? I mean, I let you do the 1 plus 2 plus to 6. And each of the probability is 1/6, right? We assume this is a fair dice, right? So each of P is 1/6. So the answer is 7/2. Again, right? On average, the phase that you see is around 3.5. And in fact, right, if you do betting, this is what you do, right? If you do betting, I mean, I lost money a couple of times in casino. I never play again. But if you actually have to bet, right? If somebody roll a dice, what you should do first? You should first compute expectation. In our case here, the expectation 3.5, right? So you should bet on either 3 or 4, because these are the closest on to the expectation of the random variables. Expectation means that on average, it's going to happen, right? Or you expect it to show that way. That's the name is very, very actually intuitive, expectation. You expect it to be that way, right? Mathematically. So it turns out that 3 and 4, right? It's actually why you get a high chance, even though you think, remember that we said this is a fair dice, right? Everybody have the same equal probability. But if I have to bet, I should bet on 3 or 4 because it's closest to the expectations. Okay, on average, it's going to happen close to the. In fact, that is also the area, right? That you have an expert here. It's going to call high dimensional statistics, concentration of measures. Concentration measure typically thinks if your random variables, right, has a concentrations, then random variable mostly happen close to the mean, right? So that's actually also the subject of the concentration of measure, which is a very beautiful, right? That's actually important for non-asymptotic analysis. We're going to look at asymptotic, which is laws of large numbers, right, on Friday. Okay, everybody, I think it's enough, good dose of introduction to probability. Okay, we have essential knowledge, and I hope that you're going to take that from there and then learn more. So the next thing that we're going to do is actually we're going to apply, right? We're going to apply. Actually, we're going to talk about one important thing is the laws of large numbers. The laws of large numbers. And then we actually we're going to go to the stochastic gradient descent, right? Hopefully we're going to finish the proof of the stochastic gradient descent on Friday. All right? I see you on Friday.